everyone, and today in this course on remote sensing essentials, we are going to discuss on this various remote sensing platforms. Though in earlier discussions very briefly we have touched about various remote sensing platforms, but in this one and maybe in future also discussions we may go deep into individual satellites and their sensors and details and all intricacies associated with them. As you know that energy source is the sun in our case, especially I am talking about passive remote sensing, and you are having satellites which are located in space, and then data collection, data acquisition, data analysis and applications are there. So, as we have also discussed that there are various platforms at different heights are possible, starting from if you go from ground. So, starting from a human is having camera at some stand or standing, that can be also a remote sensing. Then you can go for balloon, then helicopters, and then again on airborne things, maybe shuttle missions, and then finally you end up with the satellites also. So, you are having, if we come from top to bottom, then you are having satellites, though they are at a different depth in space or distance from earth. Shuttle from there from satellite downward towards the earth, then you are having space shuttles. Airborne is also possible. Then ground based remote sensing is also possible, and in between nowadays we can we have also discussed little bit about UAVs, which we will be having a complete discussion on that too. So, you are having satellites, you are having airplanes, you are having helicopters, you are having balloons, you are having drones, and of course, you come to the ground there also. So, let us take first the ground one. There are possibilities of using some cranes or some special platforms for collecting ground data, like here one example shown is mobile hydraulic platform, which can go up to 15-meter height, and you can have a payload on the top of this platform, and then remote sensing can happen. It is sometimes very useful in agricultural investigations or maybe investigation related with civil constructions also. It is also possible to go for other kind of platforms which are again ground based, like these are portable masts are there. So, there one can have on some stand or tower. One example is also shown here, that this mast is with a setup here on the ground based setup. If for very height, you can have towers like these, the greater rigidity than masts, and maybe for a very long time. Generally these are used for weather data collection and other things, but one can also have a camera or sensor on board of or top of these towers. So, it is possible. This is one schematic of these towers is also shown. So, various instruments, maybe at the lower heights you can have meteorological instrument, but at top you can have some remote sensing payloads as well. So, these are mainly ground based platforms for very specific purposes, and they are installed and are being used world over. We can also have a ground based surveillance, and generally this is radome, and in this radome basically you are having sensors or maybe antenna to receive the data, and in this particular example you can as shown here that a spacecraft or any such airborne platform is there, and this antenna which is can be inside a radome is receiving the signal. So, that is also possible, but these radomes are generally used for weather surveillance radar, and detects and tracks typhoons and cloud masses, and those are also quite common nowadays. Especially we see near the ATC this airport control towers, and they are also having radars. When we go little higher from the ground, then we can have airborne platforms, and starting with the balloons. So, balloons based very common, very old thing, and still it is being used, that you can have balloons which can go up to 20 to 40 kilometer in height, and it can be used to probe the atmosphere, different layers of atmosphere with different constituents of atmosphere, depending on the what kind of sensors or payloads you are having, and also useful to test the instruments under development. So, these things are balloons first. Suppose somebody has developed a sensor and how it will perform in space conditions. So, before that people test also in the using balloons, they also test in the airborne, and then finally these are launched with the satellites. Now, as mentioned earlier, that nowadays UAVs, or also we call them drones, these have become very common. There are few positive reasons with these devices or these platforms, is that they are now very stable, because the propellers maybe instead of 4 you can have 6, 10, or all kinds of combinations are coming, and they are becoming more powerful in sense that they can have a greater or more payloads, means they can carry more heavy cameras or sensors, as also shown here, and they can go to different heights. They are quite stable platforms, and for various kinds of remote sensing purposes these can be used. Not only here the example is shown for visible cameras, but one can have also infrared or thermal infrared cameras, and in case of natural disasters, flooding, earthquakes, landslides, or related with the crowd management, these are being used very regularly. So, even now security people or police, they too have started using this kind of remote sensing. One example is shown, that mining induced wetland contamination. So, that is being monitored, can be monitored on regular basis using drone. Another big advantage with drone is that they are equipped with GPS, and therefore, the sorties or how they will travel in the air, that can be planned and executed as per the given sorties or layout, and therefore, they can systematically cover an area giving a proper plan in geographic coordinates. So, that makes a very useful of UAV. That is why they are becoming very popular. As also one here is a UAV based photograph shown of Australia, of Wetland, and you can have, as I have mentioned, of different kind of propellers. Here this quadcopter is shown, and there are also like one mosaic is also shown here, which you can see that after getting all cameras, one can create a mosaic and complete coverage is also available. And a lot of development is taking place. If somebody is interested in more research related aspects in this drone based remote sensing, then this is the area which is very much upcoming, and one can use not only for taking images, not only in the visible, but infrared, thermal infrared, and also one can use maybe for ultraviolet, because here they do not fly at very high height. So, the atmospheric effects on ultraviolet lights may not be there. So, in mineral exploration it can be used, and also people have started creating very high resolution digital elevation models using drone based data, because overlapping or stereo pairs can be acquired with more systematic planning of sorties of drones, and therefore, then only the processing is required, tools are available, and therefore, it is possible, it is becoming possible to prepare very high resolution digital elevation model of area. There might be some negative issues are there. So, when we will discuss in detail about this, we will also discuss some minus or demerits associated with the drones. Now, airborne platforms again has been there since very long time, has also mentioned in World War II, and the airborne platforms have been used extensively. What are the advantages with airborne remote sensing is that high spatial resolution is possible, maybe up to 20 centimeters. These are relative terms and keep changing. So, today I am mentioning 20 centimeter, tomorrow might be even 10 centimeter. Analog photography is possible because earlier when we used to have aerial photography, which is not much common nowadays in India, but in other countries still it is there. Why it is not common in India? Because we are already having very high resolution satellite images, which also provides stereo pairs like from Cartosat and others, and we can prepare digital elevation model at relatively higher spatial resolution. So, airborne things we do not go, because there are certain disadvantages which we will be also seeing soon. And these easily change their schedule to avoid weather platforms. That means that with having a airborne, if weather is wet, then things can be planned accordingly when weather is clean. But in case of satellite orbits cannot be changed. So, whatever the weather conditions, it has to, it will overpass of that area and it will record whatever is available in atmosphere on the land with the satellite. But in airborne, it is possible to schedule according to clean weather. And of course, the sensor maintenance and repair is easy. Something goes bad with the sensor, then it of course, whenever aircraft will come on the ground, it can be checked, repair, and all kinds of maintenance can also be done. But with platforms like satellite based platforms, once the sensor or the satellite has been launched, sensor is on board, then this maintenance or repair, it is not possible at all. So, what are the disadvantages with the aircraft? Generally you require permission to fly aircrafts. So, permission to intrude in foreign airspace is also required, not only in foreign airspace, but its own, like in India one has to get the permission to fly airborne sensors in any part of India. So, permissions are required, and if one has to cover a large area, then many passes or many sorties would be required. But in case of satellite, it provides much more synoptic view. So, a large area can be covered in one orbit rather than airborne, where you require many times passes to cover an entire area. And because the swath is less compared to the satellite, and because satellites are very far, and these might be flying at 10 or 12 kilometer, but satellites are in space in 850 kilometer, and therefore the swath, even at the same resolution, swath may be very large. And of course, the cost relatively satellite based remote sensing is much cheaper compared to airborne remote sensing. So, these are the disadvantages with airborne platforms. This figure we have already introduced in earlier discussions, but just for advantages and disadvantages point of view, I kept this figure again here, that when we go for a space-bound platform, which is what actually this is what real satellite remote sensing is. And so, space-bound platforms, as you know, the sensors are mounted on board of a spacecraft. Various sensors even on one single spacecraft is possible. It has been going on since very long time, and one rocket can also have many satellites. Remember that few months back or about 1 year back, India launched about 104 satellites through one single launch vehicle. So, it is also possible to launch many satellites by a single rocket, and of course, the space shuttles are also involved in that one. What are the bigger advantages? The large area coverage, the synoptic view. It covers a large area, and you are having a systematic repetitive coverage because you know each satellite will have a fixed orbit, and therefore repeatability is also known. So, we know that when the next orbit will come, and so the repeatability coverage of area of interest is much stable, reliable, and one can have, whereas in airborne every time the sensor has to go in airborne, but in case of satellite it is already there, and this repetitive coverage is not for one day, maybe for 5 years, 10 years, it depends on how robust the electronics and the battery power and solar panels are on the spacecraft. So, these are the biggest advantages with the spaceborne remote sensing. In between we have been discussing about different types of orbits in which satellites are put in a space, but I will have very specific discussion here, and because the remote sensing which we are talking is a polar orbiting satellite, that slide will come very soon, but before that there are different types of satellites are there, and they too are providing some remote sensing data, especially about the geostationary satellites. So, they, as name implies, we know very well that as name implies that they are with reference to the earth, they are geostationary. That means as earth moves on its own axis, the satellite also moves along this equator. And so, as you can see that this white orbit which is shown is for the geostationary satellites. So, India is also having its own geostationary satellites. Now, these main purpose of geostationary satellite used to be for communication purpose, for telephone, for data transmission, or for television channels and other things. But nowadays they are also being used to capture images or snapshots of part of the earth, or we call as a disk. So, suppose if the geostationary satellite has been stationary with reference to India, then it will cover the India and surrounding countries, means Indian subcontinent, and in a form of a disk, because it is a snapshot. These are not typical remote sensing images, but for various purposes they are being used, especially for weather monitoring, in cyclone studies, cyclone forecasting and other things. Extensively these are being used, because you can program, you can have in every half an hour one image, or every 15 minutes an image. Also in future India is planning, I understand, that we will have even video images. So, continuously images would be coming in form of videos of the India and surrounding countries, very useful in case of weather related studies. There is another orbit which is quite similar to the geostationary orbit, which is called geosynchronous orbit, and which is, as you can see, this angle of inclination is there depending on the country where it is, because sometimes if they are far from equator, then they do not like this geostationary satellite for communication and other purposes. So, one can have geosynchronous as well, and also nowadays for navigation systems, geosynchronous satellites are also being used. Here in bracket it is written in GPS for GPS, but GPS is one part of the GNSS, that is Global Navigation Satellite System. India is also having is NAVIC or IRNSS in this category, and we are also having some satellites in geosynchronous orbit, we are also having in geostationary orbit. So, this is the geosynchronous and geostationary orbits are there. Now, the main the remote sensing for which we use these satellite or orbits, that is the polar orbit or near polar orbit. We also call as sun synchronous satellites or orbits, because sun synchronous means local time they will pass exactly on the same time every time whenever they come. So, that is why they are sun synchronous. They are not pole to pole, but little inclination is there. So, that is why they are also called near polar orbiting satellites. All your remote sensing satellites starting from Landsat to your NBSat and Sentinel or Indian satellite like IRS, Cartosat, ResourceSat, all are polar orbiting or near polar orbiting sun synchronous satellites. With reference, because they are relatively quite close to the earth, around 850 kilometer, whereas geostationary satellites are at 3600 kilometer, quite far. And of course, geosynchronous satellites are 20,200 kilometer at plus minus few hundred kilometer depth in space. So, and the purposes are different, therefore, designs of these satellites or orbits are also different. But here in this passive remote sensing, which we are discussing in this course, and further we will be discussing in this course, all we are talking about the polar orbiting satellites or near polar orbiting satellites, also called sun synchronous satellites. And this is again the similar thing is shown for sun synchronous satellites. As Earth moves on its axis or rotates, and these satellites keep moving in their orbit, and in between within that orbit the Earth also rotate. I briefly mentioned earlier about the geosynchronous satellites orbits, and they are having some inclination, and of course the distance is much more. So, this example is about the GPS, which is American Navistar navigation system. As you can see that there are 6 orbital planes are there. So, 6 types of orbits having the 24 satellites total, 4 satellites in each orbit. So, 6 multiplied by 4, 24, and you are having the distance or altitude of the satellite is 20,200 kilometer, and they are having inclination at 55 degree with each other. So, likewise these orbits are there in 6 orbital planes. In each orbit plane there are 4 satellites at equal distance. So, if I take say this red one, so one satellite here, one satellite here, another must be this one, and another is this one, and the distance wise they are having the same. So, these are the geosynchronous satellites are there. One example also shown that not only the GPS, which American system, you are having GLONASS, you are having Galileo, which is European system, GLONASS is a Russian system, QZSS is Japanese, BDS, that is Baidu, is Chinese, and of course then IRNSS, which is Indian system. So, this is the sky plot showing for that instant where these different kind of satellites were located. Here the examples of GPS is shown, example of BDS is shown, and GLONASS is also there in this dark red color or dark brown color. You are also having one satellite which is BDS 193 probably, and sometimes some other satellite also shown. These two are not so far has got any color, so they are probably not being used for that instant. The time and date, everything is mentioned here. So, GPS, as you know, having 24 satellites in geosynchronous orbit, GLONASS is having 24 again, Galileo is having 30, QZ is having not one, because they have to cover only Japan, it is not a global system. Baidu is of course global system, they are having 35 satellites, 6 in geostationary orbits, 8 in 55 degree inclined geosynchronous orbit like GPS orbits, and 7 in medium earth MEO, medium earth orbits. And let's discuss in detail about the NAVIC system. In NAVIC system 7 satellites are total in constellations, and inclination is 30.5 degree, 3 are geostationary orbit. Remember, these geostationary satellites are multi-purpose satellites. So, they are being used for communication, telecommunication, television also, broadcasting, and also for weather monitoring and other thing. But at the same time now India is also having one more duty on these for these satellites for the navigation also. So, navigation is also becoming possible. They are out of 7, 3 are important from geostationary, and they are located at different locations as shown here, and 4 are geostationary satellites in orbits of very deep in this one, and 24,000 kilometer away from there, and of course 250 kilometer perigee inclined at 29 degree. So, they come very when in the orbit time, they also come quite close to the earth as well, or you can say quite close to India as well. The design is like this. So, instead, because our system IRNSS or NAVIC is not global system, whereas GPS, GLONASS and BeiDou, these are global system. I understand in future Galileo will also become global system, but for time being it is definitely a European system, only to cover Europe. Now, various are Earth observing satellites, and this we are talking about mainly the passive satellites, which are working in visible infrared, thermal infrared part of EM spectrum, and plus one microwave, which is passive microwave, not active microwave, passive microwave. So, the first example is NOAA AVHRR. NOAA is the name of the satellite. AVHRR is the advanced very high resolution radiometer, which is the sensor on board of NOAA series of satellites. It started with NOAA 1, now we are having NOAA 19. So, in between all these satellites were there, 18 and 19 are still working, and we will have more discussion on AVHRR. And then of course, in 1972 onward, AVHRR NOAA came much earlier, but the purpose was mainly for weather monitoring for NOAA, but Landsat came for earth monitoring or terrestrial monitoring. That is why initially used to call earth resources satellite. So, Landsat 1, now we are having Landsat 8 latest. So, in between lot of Landsat satellites came with different sensors. We started with Landsat MSS, multispectral scanner, then thematic mapper, and TM, ET, then ETM, ETM plus, and OLI series, now the latest. Of course, the French also had their series, which is a spot satellite, say an abbreviation but difficult to pronounce. IRS, of course, the Indian remote sensing satellite. So, we started with this series with IRS 1A, 1B, 1C, 1D, and then we had also after that the Cartosat and Iconos. For IRS 1 after 1D, in between also some other names also came. Of course, then Cartosat, Iconos, CVIFS, GOES, and Meteosat. Meteosat is like your geostationary satellite, and Terra US satellites. These are very popular. Data of these satellites is very popular. It is being used extensively of NOAA data as well as Terra or Aqua. Two satellites are in tandem. So, their MODIS sensor is very popular for all kinds of studies, because it covers the globe. Data is freely available, and it is being used extensively for climate studies, climate change studies and other things. It is possible. Now, we will see that like ESA, the European Space Agency satellites, they earlier had ERS. Of course, this was the active, now we are having, and NVSat also had active sensors, ASAR and others, and they were providing interferometry data at very low cost for educational institutes. And now NVSat is no more functional. So, now we are having Sentinel 1 and 2. Sentinel 1 also provides microwave, active microwave remote sensing data and also interferometric data, very useful data for change detection studies, especially induced by earthquakes, flooding and landslides, all kinds of such studies, very useful. Within 35 days you get a pair, and interferometry technique can be used, and minute ground deformations can be monitored. Ground deformations, as I have mentioned, may be because of landslide, maybe because of earthquakes, or maybe mining activities, or maybe because of over exploitation of groundwater. So, lot of applications are there, data is free and a very useful data. Then Canada also had the RadarSat data, which is again active microwave data. Indian satellite, among Indian or ISRO had our RISET data, and then Japanese have ALOS data. RISET 2 is also planned, maybe next year we will have. Then ALOS, it has the sensor PULSAR, very popular satellite again. The one which I would like to emphasize about the Sentinel, currently data is available and data is free, interferometry data is available and it is really very good, and processing tools are also available, that means the software. So, one can quickly learn this active remote sensing and start applying for the studies related with ground deformations, as I have just mentioned, induced by various reasons. Now, in very brief way, we will be also seeing the Landsat missions starting since 1972, like Landsat 1, which started in July 72. It remained in space for about 6 years, 5.5 years. Then Landsat 2, which was launched in after 3 years of Landsat 1, because earlier the age of satellite was estimated about 3 years. But now, because things have improved in front of, in terms of electronics, in terms of battery, in terms of solar powers, and therefore, you would see slowly that their life is much more as compared to the. See here it is about 5.5 years, and see here it was launched in 1975 January and it is July 1983. So, about 8 years, and Landsat 3 again it is stayed about for 5 years, Landsat 4 see about 11 years. So, things have improved, the technology has improved, and therefore, the life of these satellites have also improved. Landsat 5 again March 84 and 2013, very long service, though originally these were designed only for 3 years generally. It is, but sometimes it is a normal or common thing that they will last at least for 5 years, but examples are for 11 years. Same with the NOAA series of solar satellite. But sometimes there are some mishaps also, because this is a highly risky technology in that sense, and Landsat 6 was almost a failure. Then came Landsat 7, and that was also working. I think currently it is no more. Landsat 8 is, of course, it was launched in 2013, is still working. Landsat 9 is expected next year, that is in 2020. So, life of these satellites, as you are seeing these horizontal bars, they have increased quite a lot in recent years because of a lot of improvements. Now, we will see our own remote sensing satellites. Very successful missions were there, or these satellites, starting with IRS-1A and later IRS-1V. IRS-1A was launched in March 1988, and it gave these were also designed for 3 years, but they served a lot. The IRS-1A, 1B both had the identical platforms or identical sensors also, LIS-1 and LIS-2. The repeat coverage was 22 days, and the steering capabilities was there, because the sensors had the mirror cameras. So, it was possible to change the angle of camera, and therefore, the adjacent orbits data could be required just after the wind one day. So, that was also possible with these one, and a local crossing time, that is equator crossing time or local time, was 10:30 a.m. IRS next series was IRS-1C 1D. Why next series? Because instead of LIS-1, LIS-2, it has LIS-3 sensor, much more improved sensor. Of course, it has the PAN sensor, the panchromatic camera, and the WIF sensors. It has wide angle field scanner also. Now, it was launched in 1995 Of course, it is no more working, but it has to be updated, and 1997 the IRS-1D was launched. IRS-1D had some problems, but anyway the coverage was designed for 24 days. Of course, the repeat coverage because of steering capabilities, and if you are having two satellites in tandem, you can have repeat coverage even in 5 days. This is what it was done with IRS-1C-1D. Again, local time or equatorial crossing time was 10:30. As you can see that because IRS LIS-1 and LIS-2 sensors had relatively lower spatial resolution, and therefore their swath was much more as compared to LIS-3, which had a higher spatial resolution. So, as you know that when we move towards higher spatial resolution, the swath width reduces, and this is what you are seeing here. And then a complete new series, which is ResourceSat, we launched in 2003, and it has the LIS-4 sensor. LIS-3 was very popular sensor, so it was repeated on this platform as well, and advanced AWIF sensor was also there. Again, local cross time or equator cross time was 10:30. It is same altitude, and this P5 IRS P5, or popularly known as a Cartosat, very useful because it had panchromatic capabilities, and stereo pairs were acquired, and we can create a spatial resolution DM, a 5-meter spatial resolution DM using Cartosat. So, that was very popular, and I think still it is working since then. Of course, because of higher spatial resolution, the altitude was less, and swath will also is less compared to LIS-1, LIS-2 or LIS-3. Different dates and other further details are here about like IRS-1A, IRS missions. LIS-1 had the resolution of 7.25, LIS-2 had the resolution of 36.45. So, as you go higher in spatial resolution, as I was mentioning, the swath size reduces. Here it is 148, but here 74 multiply by 2, because you can cover much more, but still it is not in 2 strips or something like that. Then you are having 22 days repeativity was same, because it is on the same platform, and channel wise also it was means spectral bands where on LIS-1, LIS-2 were the same. A very popular recent one is the Cartosat mission. It was launched in 22nd June 2016, and these details are also there. The swath, just notice the swath, because it is just 9.6 kilometer. So, very narrow swath, but spatial resolution 65 centimeter. So, with Cartosat images, it is possible to acquire images of 65 meter resolution. However, the swath is 9.6. So, if you are going to cover a large area, then you need to acquire many swath data. If it is a small area to be covered, then not a big issue. And of course, panchromatic data, but at 10 bits rather than conventional in like IRS-1D, we had sensor, panchromatic sensor, but it was working at 6 bits, now it is 10 bits. So, the radiometric resolution in case of Cartosat 2 is very good, and spectral band is of course part of visible spectrum. And NOAA series of satellites, again very popular, is still going on, and the NOAA 19 is there. It is missing here, but I know that NOAA 18 and 19 are working, and this can be updated. And I see that earlier this was TAROS series, then NOAA 6, NOAA B, NOAA 7, 8, 9, 10 and 19, they were there. And NOAA 19, as I just mentioned, that it was launched on 4th November 2008, still working, and there are 5 channels in daytime, and night time 3 channels works because visible and near infrared channel will not work. It is mainly the passive sensor, and one example of shown by the data acquired by our own satellite earth station, which is working since 2002, October 2002, and every day 4 times in a day by each satellite the data is being acquired 2 times in daytime, 2 times in night time. Why night time is possible? Because we are having 2 devoted channels on NOAA VHRR, which is channel 4 and 5 in thermal infrared part of EM spectrum. And as you know, for thermal images, in order to acquire thermal images, you do not require the direct sunlight or illumination source. Whatever the emittance or emissions which are coming out of the earth can be recorded by these sensors. So, these 3 channels works very well in night time, whereas these 5 channels, thermal channels will always work. So, one channel, this channel, this channel, and this channel, this channel, and this channel works in daytime also. This is the simple setup which we are having running, and still data is being acquired. This is the external part, which is a rotating or tracking antenna. This is a PC based system, and as mentioned, it is working since October 2002. And because the spatial resolution relatively is coarse, it is 1.1 kilometer and with the VHRR sensor, and therefore it covers a very large area. So, it covers a 2800 kilometer width of the area. I have shown the image here. So, in one go it can cover the entire India and some neighboring countries as well because of coarser spatial resolution. And this shows that whenever these NOAA series of satellite within the range of this circle in space, which is of about 3000 kilometer radius, then we can acquire, or this earth station which is called IITR satellite earth station can acquire the data from these satellites. Whatever the transmission these satellites will make, our earth station can record that one. So, that is why this circle is there. You can see that 80% or 90% of Iran and Turkmenistan, Afghanistan, Pakistan, and many large part of more than half part of China, Russia, all these countries are covered, and we are acquiring data. Of course, the purpose is different, which is I am not going to discuss that. This is one of the examples that entire Himalaya in one satellite. This is not a mosaic, but just in one swath, in one go, one orbit, and the entire Himalaya has been covered. Nighttime example also given. For the daytime example is here on the right side. This is how you see in the nighttime in thermal images, something like X-ray of the earth. So, this brings to end of this discussion, especially about the different platforms. Main focus of this discussion was on space based platforms. We have taken some examples of Landsat, our own Indian IRS series, and of course finally NOAA series of satellites. Thank you very much.